Hey everyone, and welcome back to another day of learning in the field of immunology. Today we're going to talk about vaccines and their production. So first of all, I wanted to review a little bit of the basics that we covered last lecture in immunology. So just to remind you that the immune system employs multiple mechanisms, and here they are. First being physical barriers, so again, that is skin and epithelium and everything that goes along with that in the respiratory and GI tract. And then there's innate immunity, so innate immunity being the type of immunity that has no memory and just automatically reacts when a pathogen is detected. So that's, usually in the form of inflammation. And then our third and most complex is adaptive immunity. So that is the type of immunity that has memory. And it can be divided into humoral, which involves antibodies, and cell-mediated immunity, which does not. So I'm going to go looking for my laser pointer. Here we are. So just to remind you about the major players here, these are some of these player cards from Immense Immunology Insight, one of my favorite websites. So first of all, we have our helper T cell. If you remember, helper T cells activate B cells and cytotoxic T cells to allow them to do their job, basically. So just remember that helper T cells pretty much regulate everything. They tell the T cells and the other T cells and the B cells when they can go ahead and kill things or mark things for destruction. So that's our helper T cells. And then our B cells, whose primary function is to produce and spit out antibodies, which are going to attach to the pathogens and neutralize them and mark them for destruction. And then we have our killer T cells, which will take care of intracellular pathogens by marking, or actually physically killing infected and affected cells. So that's our major players here, and you can go to that website, Immense Immunology Insight, if you're interested in learning more. Okay, so I wanted to start by talking about immunization procedures. So there are two main types of immunization, and it's important to know the difference between them. So passive immunization produces temporary immunity by transferring antibodies from resistant to susceptible animals. So you might remember in our last lecture that we talked about tetanus in a horse and having blood from one horse who has already recovered from it or who has been vaccinated against it, basically infused into another horse, and that will actually give them temporary immunity. Another example of this would be recently with the Ebola outbreak. They started taking blood from patients who recovered and giving that blood to patients suffering from the disease. And again, that was just to try to get some really effective short-term immunity. So again, immediate protection with passive transfer. So you give that blood or those immunoglobulins to an affected animal, and you're going to immediately have protection against the pathogen. So it's fantastic in that way, but it is short-lived. This is not the body itself making these immunoglobulins, so they're not going to hang around. So immune globulins are synthetic immunoglobulins or antibodies that you can actually inject into patients for, against certain diseases. We don't use them in vet medicine, at least not commonly. And then colostrum, which is something that I believe you did talk about when you were at school, but colostrum is, for certain species anyways, a hugely important way of getting antibodies from mother to babies. So babies will suck the colostrum from their mother in the first usually 24 hours or so of their lives, and then especially in things like foals, they will take up those antibodies, and they will have protection, at least short term, against a lot of different pathogens that way. Very important. Active immunization. This is the vaccination that we are familiar with, I should say. So this is administering an antigen to an animal so that it mounts an immune response. And you remember from our first lecture about immunology that there is a lag time to immunity. So if it's our first shot, it's going to happen a lot more slowly than if it's our second or third booster shot. So there's a lag time to immunity. So if an animal's dying, we might want to think about, ooh, how can we get some passive immunity to this animal? But active immunity produces long-lasting immunity. So examples of active immunization is artificial immunization, so vaccines, and you can get natural exposure. So if you are naturally exposed to a pathogen, say chickenpox, then most people, once they've had chickenpox once, are immune for life. Some people don't get quite a strong enough response and might get a second case, but most people will be immune to chickenpox for the rest of their lives, and that's an active immunization procedure. Okay, this is a diagram or a map kind of acquired immunity and the subsets of passive and active immunity. It's just to give you a bit of a visual representation of what I'm talking about. So over here we have our passive immunity, and there's two main ways of getting these. There's artificial, so immune globulins like I talked about, or there's colostral antibodies. Again, there is the other way where we actually get a direct blood transfusion, essentially, from a donor who has had the pathogen already, or a blood product. So that's another way we can get passive immunity. Active immunity, this one's a little bit more complicated because we have over here the easy one, natural infection. So that's like chickenpox, like I was talking about before. When we were kids, a lot of us got chickenpox and never got it again. That's natural infection acting as an active vaccination. Then there's artificial immunization, and this is what we do day in and day out in veterinary medicine. Active immunization can be further kind of subcategorized into living or non-living organisms that are contained within the vaccine. So living organisms over here, we have recombinant organisms. So that means organisms that are almost like the real thing, only there's been a little bit of a change in the DNA or something, and that's the recombinant organism. We use viral vectors or bacterial vectors to make those vaccines. Then there's kind of this further subdivision of living organisms. So there's genetically attenuated, culture attenuated, heterologous, and fully virulent. I'm not going to talk about any of those. Just know that there are several different ways that living organisms can be turned into vaccines that are safe. So again, recombinant organisms, probably the most common. Now, non-living organisms, killed organisms. So this is our most common other kind of vaccine, so killed vaccines. So bacterians and viral vaccines can be made that way. So basically, just like what it sounds like, the organism is there, it's whole, it's just dead. But it still has markers on its surface that allow the immune system to build up defense against it. Then we have our isolated antigens, and again, I'm not going to go into these. There's cloned antigens, toxoids, DNA vaccines, synthetic antigens. So this is just antigens specific to a certain pathogen rather than the entire pathogen itself. All right, so this is kind of our active, passive, acquired immunity. All right, so passive immunization, we talked about this already. It requires that antibodies be produced in a donor animal by active immunization, or of course by natural infection, and that these antibodies be given to susceptible animals to confer immediate protection. The protection is short-lived, as we've already mentioned. Colostral antibodies are safe. Artificial immune globulins are life-saving, but they have some risks. An example of an artificial immune globulin would be a snake bite antivenin. We don't use that a lot in our part of the world, but certainly down south and in Australia and stuff like that, they certainly use a lot of that. I'm going to talk for a minute about the ideal vaccine. So that's what this slide's all about. What we'd like to see in a vaccine, ideally, is a prolonged period of protection, a vaccine that protects both the animal being immunized and a fetus if there is one. We need something that's free of adverse side effects, so it doesn't trigger innate immunity, which means it doesn't cause inflammation or inflammatory reactions, which vaccines certainly can do. We want something that's cheap, stable, and adaptable to mass production. And this is funny because that's kind of always what we want for everything, but very hard to achieve, of course. So some vaccines have become relatively cheap, but certainly not all. They need to be distinguishable from natural exposure, so simply vaccinating the animal should not produce a positive test result. The big one in our field is FIV. So if we vaccinate a cat against FIV, then we do a snap test later down the road for FIV. It will come out positive regardless of whether the cat actually did get exposed to FIV or does have FIV. So that makes the test kind of useless. So not great. We want something that's easily recognized and used by the host. What does that mean? Well, the host's body, we should say, should recognize very quickly that this is something that it needs to mount a defense against and start doing that efficiently. But the one thing about vaccination that's never going to change, active immunization that is that it induces a slow onset of immunity. So if we need that really rapid onset, like with those Ebola cases, we have to go passive. Here are some terms to know. Inactivation refers to killed vaccines. So obviously a live vaccine is a live organism is active, and when it's killed, it is inactivated. So that just makes sense. Organisms that are killed for use in vaccines must remain as antigenically similar to the living organism as possible. Well, that only makes sense because our immune system works by recognizing specific antigens on pathogens. So we have to make sure that the immune system recognizes those antigens on these killed vaccines. If it is kind of too inactivated, which is kind of a strange concept, but if it is altered too much, let's say, it may not be recognized by the immune system, so it won't work. Attenuation is the process of reduction of virulence. So a live organism, it has a certain virulence, which is its ability to cause disease, right? So by attenuating it, we alter that ability to cause disease and hopefully make it basically zero. That's what we do with an attenuated vaccine. But again, too much attenuation, too much alteration might make the pathogen unrecognizable and make it useless as a vaccine. Too little attenuation, and herein lies the problem, may cause disease. So we have to make sure that these organisms are altered in such a way that they do mount an immune response, but they do not cause disease. It's actually a kind of a tricky thing, but it's amazing that we're able to do it. I just wanted to put a note here. A bacterin is a specific type of vaccine containing killed bacteria. So I just wanted to say that because some people come into clinics and ask about bacterins because they've read something on the internet. And if you don't know what that is, you might be a little confused, but it's just a vaccine against a bacterial disease, basically. There are merits of both living and killed vaccines. So let's just kind of go over those briefly here. So living or attenuated vaccines are great because there are fewer doses required and you don't need adjuvants. We'll talk more about adjuvants a little later in the lecture. There's less chance of hypersensitivity with these guys. Hypersensitivity is an allergic reaction. And again, I'm going to go into that in great detail in a later lecture, so don't worry too much about that. We get with living vaccines, we get induction of interferon. It's another part of the immune response, so that's good. They're relatively cheap. Smaller doses are needed. They can be given by a natural route, and they stimulate both humoral and cell-mediated immunity. They also provide longer lasting protection. So these are all really great things about living vaccines. Killed vaccines have their own kind of benefits. They're stable on storage. They're unlikely to cause disease. I would say exceptionally unlikely to cause disease. Obviously, they don't replicate because the pathogens are killed. They're unlikely to be contaminated, won't spread, and they're safe in immunocompromised patients. They're easier to store. They have lower development costs and no risk of reversion, which means that unlike an attenuated vaccine, they're not going to become active. No matter what, because they're dead. It's like we can't rise from the dead, well, neither can killed vaccines. So this is great. A living vaccine technically could mutate back to its virulent form and cause disease. So that's something that's kind of scary. Okay, so modern vaccine technology is constantly changing as new methods are developed. And this is really, really great because in the early days of vaccination, as you can imagine, there were a lot more side effects and adverse reactions. But as the technology changes, outcomes improve and the efficacy of vaccines improve. So vaccines are currently classified into 4 categories. There are antigens generated by gene cloning, genetically attenuated organisms, live recombinant organisms, and polynucleotide vaccines. The ones that we deal with mostly are attenuated organisms, live recombinant organisms, and generally killed vaccines. Adjuvants. So I promised we'd talk about this, and here it is. Adjuvants are simply substances that are added to vaccines to help improve the effectiveness of those vaccines. What they do is they increase the speed or magnitude of the body's response. They allow reduction in the amount of antigen injected. They allow decrease in the number of boosters needed. And they are actually required when you're using soluble antigens. They're categorized into 3 groups. I will tell you what they are. You don't really need to know them. There are depot adjuvants, particulate adjuvants, and immunostimulating adjuvants. Depot being the ones that we use most commonly. This over here is kind of just shows new adjuvants and what they do and kind of their benefits. I won't go over it, but suffice it to say, they just reduce the side effects associated with vaccines, increase the efficacy and duration of the protection. So they're really great, even though in the media sometimes they get slammed. They're actually safe and they work really, really well. I'm going to move on now to talk kind of just briefly of the use of vaccines in veterinary medicine, how we use them, who we use them in, why, etc. Vaccine use should be determined by careful assessment of the relative risks and benefits to an animal, and this is something that I do every single day in practice. You look at an animal, you look at its lifestyle, what it's likely to get exposed to, and also, of course, what is the kind of core vaccination recommendation for your area. I don't vaccinate animals against things that I think that they're never ever going to encounter, with the exception potentially of rabies, because it is such a deadly, deadly virus, both to animals and humans, and because in a lot of places it's required by law that animals be vaccinated against it. So we vaccinate against rabies for a different reason. It's more like population control of the disease. Not that each animal is likely to be exposed to it, but if everybody's vaccinated, then chances are it's never going to take hold. Vaccines must be administered via recommended route at the recommended dose. So always really important, if you're giving a vaccine, which you will sometimes in practice, if you're not sure where it goes and how much to give, you really just need to look at the package insert. It'll give you that information, and just make sure you follow that. Vaccines are only given as often as needed. This is very important because if we keep stimulating the immune system all the time when it's unnecessary, the immune system might start to act in ways that are not normal. They might start attacking your own body's cells and that kind of thing. It's not common, but it could happen if we keep stimulating the immune system. So, very important to only give vaccines as often as they are necessary. And remember, vaccines can cause adverse effects. There's a reading here you could do in McKernan, pages 262 to 274. I think that's a really good way to brush up on these points, and they'll go into greater detail on vaccination. There are 2 main factors that determine the use of vaccines, when we use them, and which patients. Safety, number 1. We have to make sure the risk of the vaccine does not exceed the risk of the disease, and I did talk briefly about that. But for instance, if I had a cat who never ever went outside, would I vaccinate it for feline leukemia? Well, the vaccine has become a lot safer over the last few years. However, there still is a small chance that that cat could get a vaccine-induced sarcoma. So am I going to vaccinate a cat who never goes outside against feline leukemia? Probably not. So risk of the vaccine in this case probably exceeds the risk of the disease. We have to make sure also that the vaccines do not interfere with diagnostic tests. We already mentioned FIV. So if we really need to vaccinate a cat against FIV, well, it's not commonly done, for one thing. It's not a great vaccine to begin with. But we also have to take note that we will never be able to effectively test that cat for FIV. So the second factor that determines when we use a vaccine is efficacy. Some vaccines produce a poor response. Again, I would say FIV does not produce a great response. There are several vaccines out there that really don't produce a great response, and so really we're introducing something into the animal that may not even work. So in a lot of cases, probably not the best thing to do, right? Core and non-core vaccines. So this is something that you're going to deal with all the time if you're in small animal practice and also in certain large animal practices. So core vaccines, what are they? Well, they're vaccines that protect against common diseases or I should say dangerous diseases. So that would be like rabies, right? Is a dangerous disease, but it's not common. Core vaccines are standardized. I had some handouts for this year's class, but basically you can look up online the standardized core vaccines for dogs and cats and things like that. Core vaccines for dogs include DA2PP. I think you probably all know what that is by now, but that's your distemper, adenovirus type 2, parainfluenza, and parvovirus. And rabies for dogs. So those are your core vaccines. FERCP is the only one that's core for cats. Non-core vaccines that are directed against diseases that may have a lower risk, so it depends on the geographical area. In this area, I would say Bordetella, so that's a component of kennel cough, is a fairly common one. Lyme, of course, with all the ticks that we have going on. Leptospirosis, we're seeing more and more and more of that, even within the city, because we have it's endemic in the rat population at this point. So leptospirosis is, for me, becoming almost core. So feline leukemia and rabies are considered non-core for cats, but essentially for outdoor cats. They're treated as core vaccines. So there's a little bit of debate over what should be core and non-core in certain areas, but basically we just kind of use our judgment, and each clinic will have its own protocol. And when it comes to administration of vaccines, there are a bunch of different routes. You'll recognize a couple of them, and the rest of them you'll kind of go, really? So injection, that's our most common, so either sub-Q or IM. Intranasal, so here's our lovely intranasal Bordetella vaccine going in a dog's nose. That is a very cooperative dog. I'm sure a lot of you have seen uncooperative dogs getting Bordetella. Sublingual, yeah, there aren't very many of those around. Aerosolized, same things. Mixed in feed, so for our large animal population, livestock, that sort of thing. That's a very common way of vaccinating. There's something called liquid jet, there's microinjections, topicals. These are not common. For the wildlife population, a lot of times we have kind of a mix and feed type scenario where we have like little pellets or whatever. They're like kind of like treats, so we mix them in with tasty food for wildlife, and they'll eat up their vaccines that way. So vaccines can be single antigen. So say like the feline leukemia vaccine only vaccinates against feline leukemia. It can be multiple antigen, so we can take like our FERCP, so feline, viral, rhinotracheitis, calicivirus, and panleukopenia. So that's 3 different antigens in one. So multiple antigen or single antigen. And vaccine schedules, again, will depend on the hospital policy, and they are chosen by the veterinarian or veterinarians in the practice. So this is not something that you will have to choose, but you will have to become familiar with it wherever you are. So I wanted to go over this a little bit because there's a lot of incorrect vaccine protocols going on. So I wanted to show the common sites of vaccination. In dogs, we don't worry quite so much. Distemper, Bordetella, if it's injectable, tends to go in the scruff area. Rabies, we tend to put in the right hip, and lepto in the left, lepto or Lyme in the left. So this is what I will see commonly. Also, Bordetella can go intranasal. So that's what I would say most vets tend to do. There are still a lot of old school vets that just put everything in the scruff. That's certainly not ideal because, as we know, we can get innate immune reaction to these vaccines, meaning inflammation. Inflammation can lead to other things, potentially cancer, for instance, neoplasia down the road. So we want to be careful where we put things. In cats, rabies right again, leukemia left, hind, and FERCP tends to go in the scruff. So this is what a lot of practitioners will do. However, the recommendation is not that. The recommendation is that you don't put anything in the scruff and you don't put anything in the hips. So there goes kind of everywhere that most people vaccinate. Vaccines should be given technically in the limbs, and they're also saying the tail. We did try to vaccinate a cat in a tail once, and I don't think that's something that's going to become common practice. I think 99.9% of cats would never tolerate that. But again, it is a safe place to vaccinate, so good luck. If you want to do it, great. Legs, we try to go legs with leukemia, and that's just because vaccine-induced sarcomas are more common with the leukemia vaccine than any other one, although I would say that they're a lot less common than they used to be. Horses. It's pretty simple. Horses have a beautiful triangle of muscle in the neck, and that's kind of where we tend to give everything. It tends to go IM in the neck muscle. You can give injections in the chest. Some people do that. You can do, it used to be more common to do gluteal or hip regions and hind leg or hamstring regions. You can imagine why this is not a great place to vaccinate a horse, because you kind of have to be kind of behind the leg. So safety reasons, best to stay away generally from the back end of the horse. Some people do the hind leg or the hamstring, but again, I would say most people stick up here in the neck region. Sometimes vaccines don't work. Why? Why does a vaccine not work? Well, incorrect administration obviously is a big one. I can think of a couple of scenarios. It went intra-fur, the Bordetella vaccine didn't end up in the nose, it ended up all over whoever was giving it, that sort of thing. You've probably seen those sorts of things. Failure to respond. So basically no vaccine can ever be expected to protect 100% of the population. Certain animals just don't seem to react as well or respond as well to certain vaccinations. So it's just kind of a matter of variation in the population, I guess. So failure to respond is another reason for failure of vaccination, and another one is that you had the correct administration and response to the vaccine, but maybe the animal was already infected with the disease and potentially was incubating it when the vaccine was given, or maybe the vaccine contained the wrong strain or the wrong antigens for whichever pathogen that you're looking at. A big example of that, leptospirosis. There are so many strains of leptospirosis, and in order to minimize side effects, you really can't put more than 5 strains in one vaccine. So our leptospirosis vaccines tend to contain, usually 5 different strains of leptospirosis, but certainly don't protect against all of the ones that are out there, just the ones that are most commonly seen. So that is a common cause of failure in vaccination. Something for owners to be aware of too. Adverse consequences of vaccination. These thankfully are fairly uncommon, except for the normal toxicity reactions, but they certainly are seen, and they're seen commonly enough that you need to know about them. So normal toxicities are things like transient inflammatory reactions or swelling. Sometimes fevers can occur post-vaccination, and that's because of there's certain endotoxins in the vaccine that can cause that. Inappropriate responses, so that would be allergic reactions, vasculitis, so that's inflammation of the blood vessels. It can be a pretty interesting looking reaction. Things like swollen faces you might see, so that's always kind of fun. Errors in the manufacture or administration of the vaccine. So there have been problems in the past with calicivirus, leukopenia with parvovirus, so there's been historically some issues with manufacture. And that's why we always need to keep track of the lot number on our vaccines. So when we give a vaccine, always make sure the lot number is in the animal's file. There's also vaccine-associated autoimmune disease. I sort of touched on that earlier. It's controversial, but frequent stimulation of the immune system in certain animals is thought to be linked to immune-mediated hemolytic anemia especially. So overactive immune system decides to start going after its own red blood cells. So if that is genuinely an adverse consequence of vaccination, it's really important to know about that, and again, to minimize how much we're vaccinating our animals. There's something called vaccine-induced osteodystrophy. Luckily, I've never seen this, but it has been reported rarely in some families of Weimaraners. And then I talked about this briefly, injection site sarcomas, so that's most common with cats getting their leukemia vaccine, but certainly they can happen with other vaccines in other species. So here's another little map for you, normal versus abnormal reactions. So normal toxicities, here you get your fever, malaise, inflammation, pain. This is these animals that are just kind of down and out for a day or so. That's a normal toxic reaction, so that's normal. It's going to pass on its own. We don't worry about it. Then we get our inappropriate responses, so our hypersensitivities, and we're going to talk all about these later, but allergies. The animal's allergic to the vaccine. There's nothing we can do about that. We don't know about it until it happens, unless the animal has a history of it. We get local reactions, which are the most common, so facial swelling, potentially swelling around the site, maybe hives, things like that. Anaphylaxis, rare in animals, thank goodness, but it can happen. Type 4 hypersensitivities, as you'll find out, are just delayed hypersensitivities. So granulomas, I want to mention that because it's not uncommon, especially in cats, to get a firm swelling at the site of injection, and it can last for months, usually about 3 months or so, and then it goes away. So it can look and behave kind of like a tumor initially, but then it goes away. So all of my cats have gotten these in the past, so it's not uncommon. So just be aware that that's something that can happen. If there's a lump that pops up fairly quickly after vaccination and it's firm and you're worried about it, try not to anyway. It could just be a vaccine-induced granuloma. Neurological reactions. These are really uncommon. You can get neuritis or encephalitis. I did once have a very immediate neurological reaction to a vaccine, and with supportive care the animal was fine, but it was kind of crazy to see. So things do happen, you can't predict them, you just have to be prepared. And you can get foreign body reactions, so fibrosarcoma again. This can turn into a malignant tumor, so be very aware of that. And then we always have errors as a possibility, errors in manufacture or administration that can cause pretty significant issues as well.